Welcome to the UGC lecture series. In this lecture we are going to talk about heap sort. In the last lecture we had spoken about heap and how to create a heap. In this lecture we are going to talk about the sorting of such a heap. So, as you know, we have already seen two types of heaps, the max heap and the min heap, and the two different heaps are used for sorting in the ascending order and the descending order. So, now let us look at heap sort algorithm in detail. So, the basic idea is to use a heap to sort. So, again as I have already discussed in the last lecture, the heap is represented in the priority queue data structure, and so we use the priority queue for sorting, and this can be done in the order of n log n time. So, the first set is to insert all the elements in the priority queue, and then you repeatedly remove the elements from the priority queue in such a way that they will come out sorted, and by doing 2n operations on the priority queue, each will take of the order of n log n time. So, the approximate order of the complete algorithm is of the order of n log n. Another idea here is that the sorting can be done within an array by treating the array as a heap. We have already seen how the heap can be stored in an array, and that is what we are going to use for the sorting procedure. Now, heap sort, let us look at heap sort. So, you reverse the heap property, the child nodes should always be less than the parent nodes, convert the array into an n element heap. We have seen all this before, that is the first phase, and the second phase, which is actually the sorting, is repeatedly remove maximum element from the heap and place that element in its proper position in the array, and then swap the the element at the 0th position with the element at the n minus 1th position. This is the first step. That is what we are doing is you are taking a heap and you are sorting, you are removing the element in the 0th position and swapping it with the element at the n minus 1th position. The next important step is to de-heapify this, considering only the first n, and that is 0 to n minus 1, you had n elements. Now, you re-heapify by considering only the first n minus 1 elements, and you repeat this process until the heap is reduced to 1, that is you have finished all. So, the minimum element will be in the 0th position. So, how now again I will repeat what we are trying to say. What we have is we have a heap already created. That heap will have the maximum element, it depends on whether it is min or max. So, we are assuming that the maximum element is at the root. So, what you do is you remove that, you swap that root with the n minus 1th, which is at the 0th position, with the n minus 1th position. So, that has been and output that will be the maximum element, and then you re-heapify this between 0 and n. Now, you have n minus 1 elements, that is 0 and n minus 2. Re-heapify. After you re-heapify, what will happen? The maximum element will again be at the root, take that element out and keep repeating this procedure till you have only one element, that will be the minimum element, and that will be at the 0th position. So, this is the procedure of the heap sort. So, again to repeat, idea is to keep the unsorted elements in a heap, keep sorted elements in an array, filling it from right to the left, maintain the following property: every unsorted element is less than or equal to every sorted element. This is the selection sort. This is the idea behind the heap sort. And to increase sorted path, remove root largest element from heap and put it into correct position array, restore remaining heap elements into a heap. So, this is the idea. So, how do you restore a heap? How do you create a heap in the first place? We have already seen how to create a heap, but anyway we will just look at this. So, you have another array. So, this is the unsorted elements. The main procedure of heap sort are Max-heapify, used to maintain the max heap property, build max heap, procedures a max heap from an unordered array, and heap sort sorts an array in place. The idea is that it sorts it in place, that is what we are trying to say, that we do not have another array that we need to do, we just sort it in place. So, now let us look at how to restore a heap. Now, you remove the root from the heap and then we have to see how to rearrange it into one heap. So, one approach is move bottommost rightmost leaf to the root, repeatedly swap node with the greater children until heap property is restored, that is one way of doing it. So, this is called Max-heapify a comma I is greater than left I and right I, then I is equal to left I, R is equal to right I, and you keep doing this. This is actually how we created the heap in the last lecture. The same procedure is used to do the Max-heapify, and you do it in such a way that you have created the heap all over again, except that you are not considered the last element. Now, what we have done is we have taken the maximum element and stored it in the assuming it is 0 to n minus 1, whatever is in the 0th element is the maximum element. We have stored it in the n minus 1th position. Now you have 0 to n minus 2 in the heap, reheapify that, and after you finish the reheapify position, what is in the 0th, you swap it with n minus 2. So that will be the maximum element, that will come in n minus 2. You keep repeating this procedure till the complete array is filled up again. So you actually swapping and you are doing a heap sorting in place, that is what is in the same array you are using and you are doing the heap sorting. So this takes approximately, the running of Max-heapify is just of the order of this, and where 0n describe the time to fix up the relation among the elements ai, a left I. Remember, in the heap the property is that it is stored in an array and the children will be in left of I and right of I. If you remember, if I is the node, you will have 2i and 2i plus 1 having as the children and I by 2 as the parent, this you must be remembering. So the same this left of I and right of I indicates that. 2n by 3 arises because the procedure must call Max-heapify for the subtree rooted at one of the children of node I, and children's subtrees each have size at most 2n by 3. So the worst case occurs when the last row is exactly half full. So this is the order of log n. So building a heap, we use Max-heapify in a bottom up way to convert an array a 1 to n, where n is the length of a, into a max heap. Note that all the leaves are at a n by 2 plus 1. So build max heap goes through the non-leaf nodes of the tree and runs Max-heapify on each one. So this is the building of the heap. So build max heap a, heap size a is equal to the length of a, for I is equal to length of a by 2 down to 1, do Max-heapify. So before we start, we have to initialize. Prior to the first iteration of the loop, each node is a leaf and at the root of a trivial max leaf. So the children of node I are numbered higher than I, this we have already seen. So the children of node I will have a value of 2i and 2i plus 1, and the parent of I will have a node of I by 2, that we have seen. At termination I will be 0 by the loop invariant, each node is the root of a max heap. So a loose bound on max heap is argued as follows: each call to Max-heapify costs 0 log n time, and there are just 0 n of these calls, thus the running time is of the order of n log n. A tighter bound is derived in the text, but essentially has a result that we can build a max heap from an unordered array in linear time, which we have already seen in the last lecture. So let us look at the heap sort algorithm. So heap sort A is, first you build the max heap, that is building of the max. Then for I equal to length of A, that is the total number of nodes, remember it is stored in an array A, down to 2, do exchange A1 to AI, and heap size A is equal to heap size A of minus 1, that is 0 to n minus 1 nodes, and then you Max-heapify, that is max y we are coming here because we are using a max heap, heapify that new array that you have formed. Okay. So that is how we do this, and then now let us take an example. This is an unsorted array. So you have 6, 10, 5, 12, 3, 9, 20, 2, 15, 8, 18. Then we want to build the heap. This is the heap sort, we are starting from how to build a heap. So let us look at that. So for n I equal to 1 to n minus 1, do insert Si into the heap consisting of the elements S0 to S minus 1s. Once the heap is built, S0 will contain the maximum element. We are not going to go into detail about this because we have already seen it, but so what we do here is you take the parent, look at the child nodes, whichever is the larger of the child nodes you replace it here. So you have this, then you look here, here and here, we will start with this point 12 and 3 and 6, if you look 12 is higher. So that is there. Again you have to repeat the algorithm because please note we had here, now if you take this 12 here, again this has to be satisfied heaps property. So you get this. Now if you look at this point, after, remember it is a level by level traversal in a heap, so you will go like this. So here 5, 9, but then 20 is higher, so and then that has to go up. So up to now it is following the heap property. The parent is greater than the children, the parent is greater than the children, the parent is greater than the children, but however we have not finished it. So we start here again. So if you take this gets exchanged, then 10 and again it has to go to 15. Again here if you look, these 3 and then 18 has to go. Now this is a heap. This heap building I am not talking about the algorithm in detail because we have already seen it in the last lecture. So, but only thing you have to notice, this 20th is the maximum element. So, this what we have done now is we have created a heap out of an unsorted array. Now, please note this, the heap you build has certain property, but it is not a sorted list. To get it into a sorted list, we are going to use the second phase, that is the that is actually the heap sort algorithm. Now is the phase 2. Now what you have to do is you have to repeatedly select max, do some operations till you finish the tree. So for I equal to n minus 1 down to n, do swap S0 and Si. Okay, S0 is the root node, Si is the last node, which is currently for initial stages it will be n minus 1, and then demote S0 to its proper place in the heap consisting of the element S0 to I minus 1, not I. So that is what we are doing. So now let us look at this algorithm. Remember, this was the heap that we formed. Now what you do, you have to remove 20 from the heap that you have created. So remove 20, and that is the first element, and you exchange 20 and 8. So remember, it is in an array position. Remember 1 or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually you are swapping 0 and 10. So you swap that. Okay. Now what you do, you recreate, this is the reheapifying these nodes, that is 0 to 9. Remember 10 has got 20. So 0 to 9 you have to reheapify. Now if you look at 8, 18 and 12, 18 is the larger of the child, so 8 comes here, and if you look at 10 and 15, 8 has to come in this place, and this you should not consider. So let us look at this, this is the final, remember I will explain again, these two you exchange, 18 goes up, 8 comes here, then these two 15 is larger, so put 15 there and 8 here. And after that you should not exchange it with this 20, because 20 is not considered in the reheapify procedure, a loop. So what happens? So this is what you have. Now the next step is you interchange 18 with 3, that is the next element. So this is the maximum element, so these two are exchanged and you will have 18 coming here. Now you have to heapify this part of your tree, that is 0 to 8. This was 10, this was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, 0 to 8. So you have to heapify again 3, 15 and 12, you have to take 15 there and 3 here, 3, 10 and 8 you have to interchange it with 10. So 10 goes here, 3 comes here, again you have to interchange it with 6. So that will be your modified tree. So this is your modified tree, and after this we had already reheapified the rest of the tree. Now we continue with the procedure. What we do is we take out the maximum, so or the root of the node. So 15 and 3 have to be interchanged, and this also we have already seen. So 15 and 3 we have to interchange. Now what happens? 3 comes here, 15 comes here. So this is your thing. Now what you have to do? You have to, this is 10, 9, 8. You have to reheapify from 0 to 7. So if you look here, 3, 10, 12, 12 is the maximum. So you 3 will come here, and then 3, 5, 9, 9 is the maximum. So 3 comes here. So what you have is this. Now this is the reheapified tree. Now remember, 20 is the maximum node, 18 is 20 is at 10, 18 is at 9, and 15 is at 8. Now what you do? You interchange 12 and 2. So 12 comes here, 2 comes there. So that is the next procedure. So now you have these 4 in sorted order, 20, 18, 15, 12. Now you have to reheapify from these 7 nodes. So what you do? 2, 10, 9 you interchange that, 2, 6, 8, so interchange that. So that comes to this. So this is your reheapified 0 to 7 array. Now remove 10, 10 will come in this position, swap, always you have to swap till that. So you swap, then 3, 8, 9, so 9 and 3 will be interchanged. Sorry, 9 and 3, and so I will go back, 3 and 9 will be interchanged, but if you look at 3 here, 5 has to come there. So that is done, that is the reheapifying. So now you have 20, 18, 15, 12, 10. Now you have 6 nodes which you have to reheapify. So you have to interchange 3 with 9. So again you interchange. Now you look at 3, 8, 5, 8 is the have to interchange, and then 3 here and 6 here, those two have to be interchanged. So you get, this is the reheapified 5 nodes. Now again you have to interchange 8 and 2. So you interchange. Now if you look at 2, 6, 5, 2 and 6 have to be interchanged, but then if you look at 2 and 3, 3 has to go there, 2 has to come here. So, that will be your changed node. Now, you have 20, 18, 15, 12, 10, 9, 8. Now, this is your 4 nodes. Now, you have to remove 6, interchange it with 2, swap, and then if you take these are the 3 nodes you have to reheapify. If you take 2, 3, 5, 5 comes here, 2 comes here. So, that is your reheapify. Now, you have to interchange 5 and 2. So, do that interchange. Now, you have to reheapify this. So, this comes, then after that to remove this. So, 3 is removed and then 2. So, now you have 20, 18, 15, 12, or if it is in ascending order you can take it as this is in position 0, 2, 3, 5, 6, 8, 9, 10, 12, 15, 18, 20. So, this is your final heap that has been formed. So, this is the heap sort completed. Now, what you can why we go through so much of procedure, that is, first we are doing a heap construction, then we are taking out the root node each time and then reheapifying, which means we are doing the heaping procedure all over again, reheapifying it, but still because of the fact that it is stored in an array, and the property of the complete tree means that array elements you can find out the addresses very easily, the time taken is very less, it is an array access, it is a random access. That is why this heap sort is so magically, though it seems to be a procedure that is a little complicated, since you can do it in an array inside that is, you can have an unsorted list, you can create a heap, store it in the same array and then do the sorting with the same array. So, that means the memory requirement is also very less. This is one of the important advantages of heap sort. Now, let us look at the complexity. So, first is that insert element into the heap consisting of elements 0, n minus 1. This is the heaping property, that is heap tree construction, which takes off the order of n log n, and then this is the swapping, swap S0 and Si and demote S0 to its, this is the reheapifying process. So, this also takes approximate, swapping takes only 0 order of 1, and this is the similar operation like this, because we are reheapifying, that also of the order of n log n. So, this is the now let us look at the complexity of restoring a heap, which is this part. Okay. So, that is each swap operation takes off the order of 1, as I have already told you. Swap always results in level of out of place node increasing, because what happens is you are interchanging with almost the lowest element. So, naturally you will have to do quite a lot of swapping. So, how many times can level increase in terms of n, that is equal to the number of nodes in the tree log 2n. That is why we are saying the complexity of the restoration operation is the maximum of order of log 2n. This log 2n is because of the complete tree property. So, if you have n nodes, it can have only log 2. So, the complexity of insertion is each swap is of the order of n, swap decreases level of new node by 1. So, complexity of insertion in terms of n is number of nodes in the heap of the order of log 2n. Recall that the heap creation procedure, A is an array to be sorted, start with an empty heap h for I equal to 0 to a dot length, insert ai into h, and insertion called for each element in A, so n times, each insertion cost of the order of log 2n. So, the complexity of the element of the heap creation is n log 2n, and the complexity of heap sort is, here a heap sort pseudocode for sorting array A, create heap h from A, that you remember takes n log n, for j equal to a dot length minus 1 up to 0, do remove root from h and assign it to A of j, and then you restore this heap. This restore heap again takes log 2n. So, this is the complexity analysis. First is the heap creation, that is you are given an unsorted array, what are you doing? You are creating a heap. Again remember, the heap is not a sorted array, it is an array which has certain properties. The idea here is, which I have already discussed in the last lecture, is the heap creation is in such a way that you can always find the parent and the children in no time at all, because the address is known. Node's address is I, its children is at 2i and 2i plus 1, and its parent is at floor of I by 2. And each loop iteration is of the order of log 2n, number of iterations is n. So, the total of the heap sort algorithm is of the order of n log 2n. This is the number of iterations, that is, if you have n nodes, you have to do that swapping n nodes and reheapify. The reheapify takes this much time. So, this is the complexity. So, now let us look at some of the problems that we have. You create a max heap for the following. So, you have 63, 85, 25, 30, 54, 45, 90, 15, 28, 70 and 68. Now what you have to do is, first step is you have to create a heap for this. To create a heap for this, what we do is we first initialize an array 0 to, now how many nodes does this have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what you do is you have to create a heap out of this 11 nodes. So 0 to 10 will be the size of the array, and you start with an unsorted array, then you do the heap creation. So you remember the heap, what you have to do is, if you take 63 and 85, 25, you have to take the larger of this and put it in the root. So you will have 85, 63, 25. You will have 85, 63, 25. So that is over. Then you have 63 here in the second position. The second position children are 30 and 54. It is already in the, it follows the heap property. So you do not have to do anything. Now if you look at 25, 25, 45, 90. So 90 comes here and 25 comes here. Okay. So now you have 85, 63, 25, but now this 63 has been is like that, the 25 has been replaced by 90. So you continue in this vein, and finally you will have a heap tree, and when you finish constructing this heap tree, you go to this heap, and then you have to show the steps of the heap sort algorithm. How do you do the heap sort algorithm? You take the 0th node, always you are going to take the 0th node. Okay, 0th node will be the root, and that will have the maximum value. So take out the root and then interchange that root value, 0th value, with the n minus 1th value first time, and then reheapify from 0 to n minus 2. Now take out 0, again 0th element at the 0th position, and then interchange with 0 and n minus 2, and reheapify from 0 to n minus 3, and so on. So let us take an example. Please note it is again an array operation. So if you take 0 to 10, first take out 0, I mean not take out 0, interchange the element at 0th position and 10th position, and then reheapify from 0 to 9, take out the element at the 0th position and swap it with 9, and reheapify 0 to 8, take out the element in the 0th position, swap it with 8, and then reheapify 0 to 7, and then swap 0 to 7, and then reheapify from 0 to 6, and so on till you have reached the 0th element. So this is how you do the operation, and the heap sort algorithm is one of the most sought after algorithms as far as sorting is concerned, because of two things. It has got the way you have formed the heap is in such a way that it has a property that it can be easily stored in an array, and it is an in place operation. This is very important, because normally when you are doing sorting, suppose you have a sorted array, you have to have another, suppose you are talking about 10,000 elements, okay, you have a 10,000 element sorted array, then you will have a 10,000 element array again, and then you have to do the sorting, place it in proper position. So that means twice the memory size, and if it is a very large number of elements, this is not going to be very efficient. The other problem, this is one of the problem, is general sorting arrays. This is not there in heap sort, because you are not, it is an in place sorting array. If you have one array of unordered elements, you create a heap of those elements in the same array, and then do heap sorting using the same array. So though you are doing two operations, the two operations you are doing is manipulation of the same array, manipulation of the elements like swapping, interchanging of elements in the same array. It is the first issue. The second issue is, normally when you are doing sorting of other types of sorts, you cannot use array as a data structure first of all. Okay, the problem is that you cannot use array because of the you are representing it as a binary tree. For example, if you are using binary search, we have already seen that if you are using a binary search algorithm, you cannot use a binary search algorithm for this case, because there you will have to have links and you have to have addresses, you have to go there. Here, because of the complete tree property which is used for creation of the heap, you can access the array elements very easily just by knowing the addresses of the node. You can know the addresses of the children as well as the parent, which are the two operations you need for any of this heap and heap sort, reheapifying in the heap sort. So because of that you can do that, and since this is possible, it means that the time taken also is reduced. So, it is of the order of n log n, which is a reasonably good estimated time for any sorting algorithm which you do with n elements. So, these are the two important issues of heap sorting, which is why I have taken heap sorting as an example of sorting, though there are many other sorting algorithms. We have not gone to that, the simplest of which is the bubble sort and so on. So, we have not gone into that, we have taken a special algorithm called the heap sort and explain the heap sort algorithm. Remember that even though the heap sort algorithm is a tree based algorithm, it is only visually a tree, in effect it is stored in an array, and we are doing all the operations on the same array. Thank you.